Hello, today I'm going to talk about a dihedral group of degree 9, which is a group with 18 elements, and it's a dihedral group of degree 9, which means that it's the group of isometries of the regular and the regular 9 eigen. So today I will compute the character table of this group, and this group is a semi-direct product of T with epsilon, where T has order 9, epsilon has order 2, and the action is given by inversion. Now, the conjugacy classes are easy to compute, and they are listed here. So you have the trivial class, all the classes contained in the subgroup generated by T have size 2, and they consist of the element and its inverse. And then you have the class of epsilon, which is a class with 9 elements, which are all the other elements apart from the powers of T. Now the derived subgroup is generated by T, so the abelionization is C2. So this implies basically that we can choose these representatives of conjugacy classes of the group: 1 t squared, t cubed, t to the fourth, and epsilon. And all the elements, apart from the identity, have two conjugates, except from epsilon, which has 9 conjugates. And now the first line of the character table is the trivial character, and the second line is basically deduced by inflation using the abelionization. So here the inflation is coming from the abelionization. And also there are zeros here in the column of epsilon because of the second orthogonality relation. And also the second orthogonality relation implies that here there are only 2's, or if you like, the fact that the sum of the squares of the character degrees is the order of the group, which is 18. And what is left is to fill the other entries of the table. And to do this, consider the geometrical aspect of the problem. So you can imagine that you have a regular N9 eigen, and you can, of course, what you do when you think about the dihedral group is the following, that T is just this rotation. This is what you would call T, right? Usually this is what you do. T is this rotation. And what is epsilon? Well, epsilon is this reflection. Now, why this reflection? Because you need a reflection such that it inverts T when you apply it on the left and on the right. So, for example, if you start with this point A and you reflect it, A prime, then you rotate it, A double prime, and then you reflect it again, A triple prime, you get exactly what you would get by rotating in the opposite direction. So which is the inverse of T, right? This is what you would call T inverse. And what I just showed you is that it's equal to epsilon, T epsilon, which is T to the epsilon, the conjugate, because epsilon has order 2. Now, what is the idea? The idea is that, okay, so we can get interested in this angle here, right, which is exactly this one, and 2 pi over 9, and the rotation by alpha is given by this matrix here, which has trace 2 times cosine of alpha. So we just discover that the one line will be 2 cosine of alpha, and then t squared will be the same, but instead of rotating by alpha, you are rotating by 2 alpha. T cube is the same, but you rotate by 3 alpha. And t to the 4 is 2 cosine 4 alpha. Now, what about the other characters? Well, instead of doing what I did here, you can think that your t is not a rotation of this angle, but it's the rotation of this other angle here. Oh, sorry. This other angle, which is this, okay, this is what you would call t squared, but it's not t squared, it's just a representation of a possible rotation corresponding to t. So what is the chi4? It's exactly the same, but instead of alpha, you put 2 alpha. So here you put 4 alpha, because remember that if t rotates by an angle, t squared rotates by the double, and so on. 2 times cosine of 6 alpha, 2 cosine of 8 alpha. Now you understood that basically you can do the same. You can rotate by 3 times alpha or 4 times alpha. So here you will have the rotation of 3 alpha. Let me just skip it, and then here you will have 2 cosine 4 alpha, 2 cosine 8 alpha, 2 cosine 12 alpha, 2 cosine 16 alpha, which is 4 times 4, right? Now, let me just talk about two things. The first thing is, oh look, there are zeros here. I knew that because of the orthogonality relations, but also I know that because epsilon corresponds to a reflection, and the reflection obviously has trace 0. A reflection has trace 0 because if you have a reflection along an axis and you choose as basis vectors these two vectors, then this vector here gets fixed, gets swapped, and the other gets fixed. So the diagonal elements are 1 and -1, and the sum is 0. So reflections have trace 0. And this explains all these zeros here geometrically. All these zeros here. And now we are interested in this line. And this line is just there's the other lines, but instead of alpha 2, alpha 4 alpha, we have to put 3 alpha. But what is cosine of 3 alpha? Cosine of 3 alpha is cosine of 2p over 3, which is -1/2. So 2 times -1/2 is -1. And basically here you will have cosine of 6 alpha, which is twice 2p over 3, which is also -1. Here you will also have -1, and here you will have cosine of 2 pi times 2, which is 2. And you recognize that this line is exactly the one given by inflation on S3, and this corresponds to the fact that you can draw a triangle here. Sorry. The inflation with the symmetric group S3, or if you want dihedral group of degree 3, is given by the fact that there is a triangle inscribed in this regular 9 eigen. And this is it.